characterize the notion of compactness in several ways. In this short video, we warm up by proving that compactness is equivalent to having the Bolzano Weierstrass property. What is the Bolzano Weierstrass property? Well, I'm going to define that now. Definition: let X be a metric space, we say K subset of X has the Bolzano Weierstrass property if any infinite subset A of K has a limit point in K. So this set K in the metric space X is said to be said to have the Bolzano Weierstrass property if whatever infinite subset of K you choose, it will definitely have a limit point in K. Notice that you need to consider only infinite subsets in this. Furthermore, it only says that there is at least one limit point which is in K. It does not tell you that every limit point of A is actually going to be in K or any such thing. No such assumption is made. Just one limit point has to be there in K. Now, one more comment, as you could have guessed from the definition, any finite set is automatically going to have the Bolzano Weierstrass property. I urge you to think of more examples in the setting of the real numbers and in Rn, which are the most important metric spaces for our purposes. Anyway, what I'm going to prove now is the fact that compactness and having the Bolzano Weierstrass property are equivalent. Let X be a metric space, then the set K subset of X is compact if and only if it has the Bolzano Weierstrass property. So what this says is checking whether a set is compact. So again, I keep forgetting the adjective. This is sequentially compact. Okay, they're all the same. I'm not just being lazy and forgetting. It's just that subconsciously I've already identified all the various notions for metric spaces. You will also be in this position a couple of videos down the line. Till then, we have to be a bit careful and write sequential compact. So set is sequentially compact if and only if it has the Bolzano Weierstrass property, and the proof is rather short. So let's begin the proof. Now what I'm going to do is I'm first going to show that any sequentially compact set must necessarily have the Bolzano Weierstrass property. So suppose K subset of X is sequentially compact, and let A subset of K be an infinite set. Now I have to show that some limit point of the set A is contained in the set K. So what I do is let Xn be a sequence of distinct elements of A. Okay. Now, why does such a sequence exist? Because we are assuming that A is an infinite set, we can definitely find an infinite sequence of distinct points. By sequential compactness, some subsequence some subsequence x and k converges to x, and this x should be in k. That's the definition of sequential compactness. Now it is trivial to see that x is a limit point of A. Okay, so this part is rather just apply the definition of sequential compactness and you get what you want almost immediately. Now on the other hand, assume that K has the Bolzano Weierstrass property. I'm getting tired of remembering the correct spellings of Bolzano and Weierstrass, so I'm just going to write BW property for the sake of not making a typographical error in the name. Okay. Now let xn in K be a sequence. Our goal is to exhibit a convergent subsequence of xn, and this subsequence should converge to a point in the set K. That's our goal. Now there are only two possibilities. There are only two possibilities. The first property says the underlying sequence comprises only finitely many elements. What this essentially means is that this xn set is a finite set. You put all the terms of the sequence inside a set and you get a finite set. That's one possibility. In this case, it is trivial to extract a constant subsequence. So if finitely many terms just keep repeating, at least one term should keep repeating infinitely many times, and that will give you this constant subsequence, which is obviously converging to a point in K. So that's one possibility. The second possibility is this set xn is an infinite set. Okay, and xn being an infinite set, immediately by Bolzano Weierstrass property, we can find a point x in K such that x is a limit point. Of this set xn. Note, this is a limit point of the set xn, not, I repeat, this is not a limit of the sequence xn or any such thing. Okay. Now from this, it's rather easy to extract a subsequence. I'm going to leave that to you as a straightforward exercise, but let me just give you a hint. If you look at this bx 1 by n, this ball of radius 1 by n, this contains infinitely many terms. So let me not use k, let me not use n, let me use k instead. Take this ball of radius 1 by k. This contains infinitely many terms of xn. Okay, the sequence xn, infinitely many terms of the sequence xn has to be there in this ball. In fact, that's the characterizing property of a limit point. So from this, it should be rather straightforward to extract the required subsequence that converges to x, showing that any sequence has a convergent subsequence in K, hence K is sequentially compact. Now in the next video, I'm going to formulate compactness in terms of open covers, so stay tuned for that. This is a course on real analysis and you have just watched the video on the Bolzano Weierstrass property.